Hello and welcome back to the channel. In this video, we are going to review chapter 3 of the Salvadori Structure in Architecture textbook. So chapter 3 is about structural materials. And let's take a look at the first section, that is the essential properties of structural materials. And as we know, there is a wide variety of materials that are used in architectural structures, such as stone, masonry, wood, steel, aluminum, reinforced and pre-stressed concrete, plastics, and some high-tech materials such as carbon fiber, for example. So what they all have in common is the essential properties that make them suitable to withstand loads. So, whether the loads act on a structure permanently, intermittently, or only briefly, the deformation of the structure um, must not increase indefinitely and must not disappear after the action of the loads ends. So, the distribution of load or force over the area is referred to in engineering terms as stress. You already know that, which is the same as the more conventional term pressure, measured as force per unit area. So a material put into tension will experience tensile stress and stretch, and conversely, a material placed into compression will experience compressive stress and contact. And contract. Stress is one of the most elemental and important concepts in structural mechanics. It will therefore frequently be referred to for the remainder of this book. And you remember that there are 15 chapters here in this book, so we'll get back to this concept frequently. So, understanding the concept of stress is one's daily life experience is intuitive. For example, the blow of a hammer on a nail will drive the nail into a piece of wood, but the blow of the same hammer directly on the wood will not similarly embed it into the wood. This is because the force of the hammerhead is distributed over a much larger area. So, with the same force, the stress is much lower on the hammerhead, for example, than on the tip of a nail. So, when you refer back to the textbook, you can see this experiment that is called a bed of nails. So, and you'll see how that actually performs. So, although a single nail pressed on by one's full body weight would easily pierce skin, when the same weight is distributed over many hundreds of nails, the force becomes so low that one can safely rest on a bed of nails without being injured. So, a material whose deformation vanishes rapidly with the disappearance of the loads is said to behave elastically. All structural materials are elastic to a certain extent. If they were not, and the residual deformation were present in the structure after unloading, new loadings would gradually increase this residual deformation and the structure would eventually become useless. So, and please take a look at some of the examples here. There is a snowshoe as well. So that allows to actually distribute force over a large area, and the pressure is then reduced to the point that one may walk on soft snow without actually penetrating deeply through the surface. So please refer to the images. There is the linear elastic behavior. Those diagrams I would like actually you to get familiar with. So most structural materials are not only elastic, but within limits are linearly elastic. So this means that their deformation is directly proportional to the load. So these concepts may be visualized by examining a force deformation diagram. And please take a look at that. So on the y-axis, there's force, and on the x-axis, there's the deformation. And you can see the curve, you can see the elastic range and the inelastic range. So please just refer to that, and I would like you to actually remember how that works. So while the force deformation diagram provides an easy visualization for the structure in tension, the amount of deformation is dependent on the magnitude of the force and size of the member. In order to make the diagram independent of these values, they are normally plotted as a stress strain diagram. And again, please refer to the book. You can see stress is on the vertical axis and strain on the diagonal, and you can see excuse me, on the horizontal, and you can see that diagonal line. You can see how concrete is tested in compression, how aluminum is tested, how structural steel is tested. So those are different diagrams that are shown here. So, materials such as structural steel behave plastically above their elastic range and have a clear and well-defined yield point. Other common building materials, such as aluminum and concrete, do not have such a well-defined behavior or even a clear yield point. For such materials, a yield stress is empirically defined based on a specific strain amount. So materials to be used for structural purposes are chosen so as to behave elastically in the environmental conditions and under the type of loads to be expected during the life of the structure. So the importance of this requirement can be illustrated by a simple example. And here, please refer to the images, and there are wax candles that actually change their shape based on the temperature. So if a wax candle is improperly inserted in a candlestick, the seemingly stiff candle will slowly bend out of shape in a warm temperature. And after a few weeks or months, depending on the temperature and type of wax, may be completely bent over. So you can see that, and that is just one of the examples. Um, so um, Materials that are linearly elastic up to failure, such as ordinarily annealed glass, the type used in the picture frame, for example, just the regular glass that we face every day, and some plastics are highly unsuitable for structural purposes. They cannot give warning of approaching failure and often shatter under impact. Recent developments, however, that combine the flexibility of plastics and the strength of glass have led to exciting architectural developments. So, for example, laminated structural glass is comprised of sheets of high strength tempered glass combined with resilient plastic film fused into multiple layers. Its strength and flexibility is such that it can be used in applications such as beams and floor slabs that have previously been impossible. So, and you can take a look at the pictures here and how the brittle failure happens, and you can actually see the laminated structural glass, like how that looks like in the section. So, steel at nominal temperatures has the useful linearly elastic range up to the yield point, followed by a long plastic range. So, it will, however, become suddenly brittle at a temperature of negative 30 Fahrenheit, which is minus 34 Celsius. So, and some unexpected failures of steel bridges in Canada in the 1950s were traced to this sudden transition from elastic plastic to brittle behavior at low temperatures. So, and there is an example of the Wolf Trap Performing Arts Center in Vienna, Virginia. So you can take a look at that. There are pictures of that, and there's like a little case study as well. So you can see an example of the brittle fracture of a steel beam. So some materials have a relatively limited elastic range and behave plastically under low loads. So certain plastics, thus correctly named in this case, flow under almost any load. And please take a look at, for example, warping of steel due to fire. So while unprotected steel will not burn in a fire, at around 1100 Fahrenheit, it substantially loses stiffness and will warp like plastic under its own self weight. It is notable that this loss of stiffness occurs more than 1500 Fahrenheit below its melting point. So that's good to know if you want to test the materials for the fire safety. So modern structural materials such as steel are what are known as isotropic from the Greek isos, meaning equal, and tropos, meaning direction, and homogeneous. That is, their properties and behavior under load are the same throughout the structural component. So because of this, their resistance does not depend on the direction in which they are stressed. So um, then let's take a look at some other new materials here. So for example, the engineered wood obtained presents more homogeneous strength characteristics and moreover can be made weather resistant. Also, many varieties of engineered lumber are now widely available, such as plywood, OSB, particle board, medium density fiberboard, or MDF, then glulam or glued laminated timber, and PSL or parallel strand lumber. So each of these not only improves upon the properties of natural wood, which is subject to the variations that accompany any organic material, but of increasing importance allows the use of small pieces of leftover materials that would formerly have been waste, thus making better use of resources. So we always need to think about sustainability as well. And again, a few nice images showing compressive stress and shear stress. And let's actually move on. Let's take a look at the material constants and safety factors. So, for structural purposes, materials are mostly used within their linearly elastic range, and this implies that their deformations are proportional to their loads upon them. So, but different materials deform differently under the same loads. So, for example, steel will act differently than aluminum, and it will definitely act different than wood. And you can see the tensile deformations here. So steel is stiffer in tension than aluminum, and the measure of the stiffness is a property of each structural material called its tensile elastic modulus. The higher a material's elastic modulus, the stiffer it is, meaning that it will not stretch or deform less than a material having a lower elastic modulus. So it is seen on the diagram here. Please refer to the figures here that aluminum does not have a well-defined yield point. So I would like you to actually take a look at those examples. There are a few case studies here, so please just go back and check that. We're not going to cover that in the video because there are a few, um, like it will be too much for the video, but it is really, um, the graphical representation is really good. So please refer back to the textbook. So the load or combination of loads inducing stresses equal to the ultimate strength of an element, and that is called the ultimate load for that element. When the design of a reinforced concrete structure is based on ultimate strength, an approach called strength design, codes specify that certain load combinations should not reach values higher than the ultimate load. So please remember that when you do your strength design calculation. And we are moving to the modern structural elements. So heavy timber structures often employ iron in steel, tie rods, and sag rods. So the function of the sag rod is simply to prevent the tie rod from deflecting under its own weight. The sag rod serves no other structural function unless a large object such as the chandelier is suspended below it, in which case it transferred that weight up to the top timber members. So the purpose of the pilasters is to provide a good bearing surface for the truss and to strengthen the walls. And please check the diagram here. It shows wood and iron trusses and how that supports the roof and the whole structure. So, increased knowledge in chemistry and physics has substantially improved the properties of structural materials during the last 150 years. Stainless steel has all but eliminated the danger of rust in most applications, while rust-resistant steel, such as the U.S. steel corten, also known as weathering steel, stops rusting after 2 or 3 years and does not require painting. So this tough, rough rust coating acts similarly to the oxide coating that aluminum develops, both of which form a protective layer that inhibits continued corrosion under ordinary usage. So also what is important to remember here is we already spoke about that in the previous chapters. You know that concrete is very strong under compressive stresses, and the continued use of ancient Roman structures such as the Parthenon, and you know that to this day, the largest unreinforced concrete dome in the world that is still functional. So that gives the testament to its durability when used in a compressive manner. So under tensile stresses, however, concrete is very weak and breaks easily. The reinforcing steel therefore acts like a web of tensile elements, which pervades and holds together the mass of concrete. So also it should be noted that concrete does not become hard by drying out. In fact, moisture is a critical component of the hardening process, which is actually a chemical reaction known as hydration. So during hydration, or as more commonly referred to the curing process, heat is produced, and unless the concrete is properly protected from both low and high temperatures, it may set improperly and crack or have an ultimate strength lower than its design strength. Cracks due to the drying shrinkage may permit humidity and water to reach the reinforcing steel, which then rusts and eventually disintegrates the entire reinforced concrete mass. So, therefore, it's a critical part in the process that each batch of concrete placed in a building, bridge, or other construction project must be tested to guarantee that its strength is in an agreement with the lab design and and it's going to be properly cured in a moist and temperature controlled environment. So, in here, let's talk about manufacturing of concrete. So, you know that that is a delicate process that requires as much care as that of any chemical. So, the concrete for important construction jobs is seldom mixed at the site. It is manufactured off-site in concrete plants and transported to the site. So, um, on the other hand, because concrete properties vary so much with composition and methods of mixture, many different types of concrete can be obtained, each suited for a specific purpose. So, concrete with a compressive strength as high as 12,000 psi, rapidly hardening concrete, and concrete with lightweight aggregates are constantly being introduced. So, in addition, chemical admixtures of many types, such as improving weather resistance in freeze-thaw cycles, or yielding a speeding up or retarding of curing time, and those making the mixture more flowable and easily pumped up many stores. So those are also under continual development. And probably by the time you're watching this video, a new way of reinforcing the concrete or curing the concrete has been introduced. So it's always improving, and there are always some new ways to do the same thing. So, the oldest and still most common method of reinforcing a beam, referred to as conventionally reinforced, provides steel that acts in a passive manner. With a steel rod, when a steel rod is inserted in the lower portion of a beam, it is in the region of tensile force on the beam and tightly bonded to the concrete. The reinforcing steel, colloquially referred to as rebar, is stamped with ribbed patterns to ensure a good bond between the concrete and steel, and essential transfer of force if the steel is to carry loads from the concrete. So, in bending under a load, the concrete engages this tensile steel and prevents cracking. So please refer to the diagrams here. Just that is something really important that you need to remember. So there are two methods of creating pre-stressed concrete. The difference between the two techniques has to do with when the pretensioning occurs. So one type is referred to as precast, pre-stressed, or more commonly just pre-stressed, and the other one is post-tension. So pre-stressed concrete is created in factories for the prefabrication of structural elements. In tendons or exceptionally strong wire are pulled against the ends of steel forms in which the concrete is poured. Once the hardened concrete grips the tendons, these are cut from the formwork ends, and their tension puts the concrete in compression as the tendons naturally attempt to return to their initial unstressed position. So, and when we talk about post-tension concrete, slack tendons are threaded through hollow sleeves known as ducts set in the concrete form, and once the concrete reaches a sufficient strength, are pulled against the hardened concrete by outside jacks, thereby compressing it. So post-tensioning is used mostly on site and in large structures may proceed in stages as required by the stresses in an element, which increases under the increasing dead load. So again, please refer to the images that will be easier for you to understand the concept. And there is a nice image of Cathedral of St. Mary in San Francisco, California. You can see the exposed structure here. You can see the hyperbolic paraboloid roof, and you can see the ferrocement tiles following the profile. So it's a very interesting structure, and please just take a look at that. And that was it. This wraps up our chapter 3. So thank you so much for watching. I will see you in chapter 4. Thank you.